Hello there. My name is Jordan. I'm going to be talking to you guys today about the tornado warning problem. So basically, whenever you hear your tornado sirens go off, like what sort of things go into that decision? Is there just some sort of dude just sitting on a high, tall building, looking out and going, "That storm's worth a tornado warning," or is there, a little bit more going on there? What sort of information do you guys bring in to try and make these sort of decisions, and who's making these decisions? So. Before I get into that, I want to tell you guys a little bit about myself. I did my master's at the University of Oklahoma, and I studied meteorology. And while I was there, I got the opportunity to do some professional storm chasing. So there are guys that work at research facilities, specifically NOAA, is the big government one you guys may have heard about. And there's a smaller group within NOAA called the National Severe Storms Laboratory, and that's the one that I got to work with. My advisor basically was the project lead for this huge project called Taurus. And I'm going to give y'all's teacher a whole bunch of links and stuff, so I'm going to reference some things throughout this talk, and you guys can look up these things when I'm done talking. I worked for NOAA and NSSL, and basically I got to drive a truck and deploy um, these little things right here. It's called a mobile radiosonde. So these go up on basically those big weather balloons. We attach them to those. They fly up in the sky, and this sends us back information like temperature, humidity, things like that. So we get information about the atmosphere near really severe storms was the part of that project or point of that project. Basically, we got pretty close to tornadic supercells. We'd hop out of the truck, attach these things to balloons, let them go. Um, Hopefully they go up pretty high. And we got a lot of information about the near storm environment. That was really cool. So, so that's me. Uh, I currently work for the University of Texas doing something a little bit different, but I spent I think like 4 or 5 years storm chasing, and so that's why I'm talking to you guys about the tornado warning problem today. So before I get into um, really that the decision of do we warn an area that a tornado is coming, I kind of want to get into the storm theory and sort of like what do storms look like, why are they happening, and all that kind of stuff. So let's go to the board. I'm not going to get dressed up for this kind of thing. Okay, we're at the board now. So there's really four things that go into creating a severe storm. And real quick, I want to sort of make this clear that there are a whole bunch of different kinds of storms. You can get little tropical rain showers or snowstorms, and the mechanics behind all those are a little bit different. So I'm specifically talking about like tornado producing severe weather that you guys would experience here in Oklahoma. So there's really four things that you need to get a storm like that. First thing's moisture, which should be kind of obvious. Storms rain, so you need water, right? The second thing is lift. So you need something to kind of take this air that's near the surface and shove it up into the sky. That upward motion is really what gets storms going. And if you have that strong upward motion, your storm is typically like strengthening. Upward motion is a sign that a storm is getting stronger or is strong. Instability, this one's a little weird, but basically once you get the air going upwards, it continues to want to go upwards is the idea for that. This one can get a little confusing and weird, but basically it's kind of tied in with lift in that it helps air go upwards. Now the thing that's really interesting for the storms that happen in Oklahoma is the wind shear. And what this means is, here I'll come to the board real quick. Whenever you get this strong upwards air, right? It's called an updraft. If you don't have any wind shear, and when I say wind shear, I mean that basically the wind speeds get really strong as you go up high in the atmosphere. If you don't have that, let's just say it's kind of boring. There's not a whole lot of wind going on. You just get some upward motion, not really a whole lot side to side. What will end up happening is you have this impulse. You'll have the storm go up. Then everything up here will get really cold and heavy because of all the water and the clouds. It's cold up there in the upper atmosphere. This will just get really cold and fall back down because cold air is pretty heavy. And what ends up happening is your storm will go up and it will collapse on itself. And this is what happens a lot of times in the summer. You'll see a little storm go up, it'll rain for like 5 minutes, and it'll just die. It's because the updraft and the downdraft aren't separated from each other. So it's essentially, you get cold air falling into a region that's usually kind of warm. So if you do have wind shear, let's say you've got a lot of wind up here, what'll end up happening is that updraft will get sort of separated from the rest of the storm. You'll get something that looks sort of like this, where it kind of blows off to the side. And what will end up happening is cold air up here, you get a bunch of rain and cold air falling. But the point is that this now happens somewhere else. It's not happening in the same region that you're getting this updraft. This is this warm air coming in. So this is this impact of wind shear. Is it whenever the air comes up into the storm and feeds the storm, it'll fall down somewhere else. And because of that separation, you can sort of just continue with this cycle of like feeding the storm, dropping the cold air out. And this will essentially go on until, you run out of moisture or something goes away and the storm will end up dissipating. But these are how you get those really intense, really strong storms that end up producing the tornado. Now, a quick moment on what a tornado is. Let me erase this real quick. Okay. So the interesting thing is that these storms a lot of times will rotate really high up in the air. They'll spin. So it's kind of logical to think, okay, these storms are spinning, so they kind of just like suck down to the ground, and maybe that's what a tornado is, right? You just get the spinning motion, goes down to the ground, and now you've got this intense little, tornado thing. The issue is that the air is traveling upwards. So the idea of like something coming down onto the ground from above is a little weird, right? Because all this air is moving up into the storm. It's not coming down. So really what ends up happening is that near the surface, near the ground, we're talking, where the trees are, basically, where all of us are, you'll get some spinning air that gets yanked up by the storm. And that yanking motion can kind of bring that air together and make it spin really intensely. So I don't want you to think that like the tornado comes down from the sky and, starts spinning. It's really actually that whenever you have the storm present, you can take this air that's already kind of spinning and really bring it together and concentrate it. And that's what ends up happening with the tornado. So that's sort of why like you can get really strong, intense storms that don't end up producing tornadoes because you don't have this little spinny stuff at the ground going on. These they're related, but you don't get a tornado all of the time. So that's what's actually creating the tornado. Okay, sorry if this is a weird, different interface, but I'm using Zoom for this because I'm going to show you guys some stuff that's on my screen. But now that we've talked about storms and kind of how they come about, I sort of want to get into what techniques we have of like actually knowing that storms exist. I mean, let's say there's a storm out in western Oklahoma. How do we know that it's there besides driving out to western Oklahoma and going, hey, look, there's a storm there, right? So like, what sort of observations are we making of our environment just with like, routine instruments? So before I get into this, I wanted to show you guys a quick video, and I will share my screen here, that was recorded during my field mission. And this kind of shows you guys what, number one, a weather balloon is, because we're going to talk about that in a bit. And you'll get to see what kind of environments they are launched in. So this is me here on the right-hand side, and this is my advisor and a co-scientist of mine. And this big sphere here is the weather balloon that we're going to try to launch. Now keep in mind this is near a supercell, a really strong thunderstorm. The winds are very strong, as you will see. So let's watch. So we take the weather balloon out. We're walking back onto the road to get clearance away from the trees. Of course, I'm looking to see if there are any cars coming. And whenever the scientist was in the clear, she let go of the balloon, and the wind just rips it out of her hand and takes it off. And notice these trees and the power lines here. This is a pretty chaotic weather balloon launch. A lot of times they're a bit more calm. And so this is an example of a time where this is what you would think of for a routine radiosonde launch. Is just nice little weather balloon, clear skies, pretty day, let it go, float straight up, and it takes a bunch of measurements. Now, the United States government has paid for these to happen all over our country twice a day. And if you look here on the left-hand side of my screen, okay, sorry if this is a weird, different interface, but I'm using Zoom for this because I'm going to show you guys some stuff that's on my screen. But now that we've talked about storms and kind of how they come about, I sort of want to get into what techniques we have of like actually knowing that storms exist. I mean, let's say there's a storm out in western Oklahoma. How do we know that it's there besides driving out to western Oklahoma and going, hey, look, there's a storm there, right? So like, what sort of observations are we making of our environment just with like, routine instruments? So before I get into this, I wanted to show you guys a quick video, and I will share my screen here, that was recorded during my field mission. And this kind of shows you guys what, number one, a weather balloon is, because we're going to talk about that in a bit. And you'll get to see what kind of environments they are launched in. So this is me here on the right-hand side, and this is my advisor and a co-scientist of mine. And this big sphere here is the weather balloon that we're going to try to launch. Now keep in mind, this is near a supercell, a really strong thunderstorm. The winds are very strong, as you will see. So let's watch. So we take the weather balloon out. We're walking back onto the road to get clearance away from the trees. Of course, I'm looking to see if there are any cars coming. And whenever the scientist was in the clear, she let go of the balloon, and the wind just rips it out of her hand and takes it off. And notice these trees and the power lines here. This is a pretty chaotic weather balloon launch. A lot of times they're a bit more calm. And so this is an example of a time where this is what you would think of for a routine radiosonde launch. Is just nice little weather balloon, clear skies, pretty day, let it go, float straight up, and it takes a bunch of measurements. Now, the United States government has paid for these to happen all over our country twice a day. And if you look here on the left-hand side of my screen, I hope that's what y'all are still looking at. Let me make sure. Okay, yeah, screen sharing. Screen sharing. Make sure. Okay, now I've made sure that's on the right one. So on the left-hand side here, where these stars are the locations of these radiosonde launches twice a day, every day, which looks good. Like when you first look at this, you're like, cool, we have a nice spread of everything. Awesome. If you notice here, let's say the state of Oklahoma has one. The state of Kansas has two. Same with the state of Nebraska. So you can imagine that this weather balloon is measuring literally like the air that's right next to the measurement device, and trying to say that that represents the air across half of a state. So that's a bit of a problem, because weather, as you guys know, weather can change very rapidly. I mean, you guys have experienced cold fronts. It can go from warm to really cold over a pretty short distance. So having one measure, two measurements per state is not a whole lot to go with. I will say that combined with weather models, we can get a lot of information out of that, but there's a sort of a problem in meteorology that we don't have a lot of observations. We're always in sort of this mindset that we could collect more information about the environment than we have. We certainly could have more information. So in that vein, Oklahoma, which is a wonderful place to study weather, the state government of Oklahoma paid for the Oklahoma Mesonet, which actually I'll click here. The Oklahoma Mesonet is a continuum of surface observations. So they're like stations with like a temperature, humidity sensor, things like that. And they're all over the state in all of these different locations. So instead of having 2 observations per state, we have like, I think there's about 100 of them. I think if you add up all those numbers here in the legend, you get about 100. So it's awesome whenever weather happens in Oklahoma, because we have a lot of observations of what's going on. We can tell where the cold front is, where the warm front is, all these different boundaries that might be important. You can see them with a lot higher resolution in Oklahoma than you can other places. And like I said, I live in Texas now, and it's sort of frustrating because whenever weather happens, I don't have that same resource to go look at, where exactly is the cold front. You sort of have to use other methods to get a feel for that. Some of those other methods are using satellite. So what I have here is a clip from the GOES 16 webpage. This is a NOAA.gov webpage, and you guys will have a link for this. What I've clicked on here is the southern plains, and this is geocolor. So this is basically just like what the planet looks like. There's no image processing done to this. So this is from this morning, which is just December 15th. And we had a cold front passage, and you can sort of see that banding here with this really cold, dry air behind that cold front. And so this is a wonderful way to get a feel for what's happening on a large scale. You can't really see what's going on the ground. You can't see inside of the clouds, so it's not complete information, but you do get a feel for where these large structures are, sort of their characteristics, just by looking from top down on the satellite. And like I mentioned earlier, there's a lot of image processing that can be done to these, so you get more information than just what do the clouds look like. Sure that you can get that from a satellite, but you can get a lot more things like temperatures, water vapor. So there's a lot of information that does come from satellites, which is pretty awesome. Now, we also have radars, which you guys have probably seen quite a bit of that, and so I'm not going to show you there. So it's really like those mesonets, those soundings, the satellite imagery, and those radars all come together to give scientists and meteorologists the observations they need of the storm to make these decisions. Now, like I said, these observations are not very dense. It's not like they happen all over the place all of the time. So there's a lot of, well, we have this observation over here and over there, and our storm's in between them, and we're trying to come up with some sort of decision of what the environment's like. And that's where weather models come in. It's where we take those observations and then we apply a bunch of physics to them to try and guess what's happening somewhere other than where we have the exact observation. And while weather models are certainly not perfect, they're surprisingly good, I think is what I would say. I was pretty skeptical when I went into school because you have 50 radio sound observations over the whole United States, and somehow you're supposed to figure out what a storm is doing that's the size of like a small town. So it's a difficult problem to deal with, but these weather models are quite powerful, and they do a pretty reasonable job. So I just wanted to go through some of the weather models today. I don't know if I hadn't looked at weather models before I went to school, and so I kind of wanted to give you guys an opportunity to see what they look like and kind of play around with them. So this website is one of two websites that I use quite extensively. It's from the College of DuPage. This is a meteorology school if you guys are interested. And you can come to the weather analysis tools, click on numerical models, and it brings up this page here, which all of these different acronyms are different kinds of weather models. I'm not going to get into the specifics of the differences between them, but they are different. Now, one of the better ones to use as far as if you're looking at severe weather is this HRRR, or the HRRR, and you can click on a specific location and you get all these different things here on the left hand side, most of which don't make any sense to you guys, which is totally fine. Half of them don't make sense to me, honestly. But what you could do is you come down here and go, well, I'm interested in the precipitation products, and maybe I want to look at the simulated reflectivity. So this is basically that future radar that you guys see on the TV. And you come here and go, oh, okay, it looks like we have a storm today. It's going to be raining, right? And you can play this little slider here. You'll go forward in time, backward in time. You can kind of check out different times. And like I said, a bunch of different stuff. If you want to see what's the temperature going to be like, you can click on that and go, oh, okay, in a few hours, the temperature is going to be just about freezing in Oklahoma City. This is just kind of fun to play with. If you guys want to get on a website, check this stuff out. I think it's pretty cool. Relative humidity, whatever you want to look at. Pretty humid. Okay. So that's really sort of the talk about just like the observations and the weather models. So this is really like all the information that's coming into a forecaster. So really you've got a guy sitting at the National Weather Center, which is where I went to school down in Norman, sitting at a computer, all this information is coming into them, and they have to make a binary decision, a yes or a no, if they're going to warn a particular storm and say, hey, there is a tornado coming in your area, take shelter, right? Now, as you guys know, there's a lot of reasons why you want to be careful about that decision, right? You don't want to just go into it and go, there's a storm nearby, everybody hide, because there's probably not going to be a tornado, and if you do that, enough people are going to stop listening. So there's this idea that we only want to warn storms that we really think are going to be a problem. Like, this stands a high chance of producing a tornado. We're going to go ahead and tell all these people that they need to take shelter. Now, this is sort of where science and society kind of come together and don't exactly fit up very well, because storms are relatively localized, right? Like, they're not that big at the end of the day. These tornadoes are the size of like maybe a city block at best. So whenever you go to warn an area, typically that area is defined by a county. Whenever you go, I want to warn this area, you have to warn the entire county. That's sort of just how the system's built. Typically, only a very small portion of that county is actually going to be impacted by the tornado. So you really need to be confident that I'm going to have a tornado in this county that's definitely going to impact people. Because if you're not sure about that, you may just be warning a lot of people for no reason, which is frustrating. So especially in an area like Oklahoma City that's very populated, you only want to make this decision if you absolutely have to warn these folks. So what goes into that decision, right? All of these observations, all of these soundings, the radar, the forecasters are looking at this all real time, and these weather models sort of help them, predict what could happen in the future, right? Because whenever these storms pop up, these guys are usually aware hours beforehand that this is going to happen, right? They know that there's probably going to be some pretty bad storms in the area today. They can get that from the observations alone. But what they don't know is, where are the storms specifically going to happen, and where are they going to go specifically, which these things happen on very short time scales. It's hard to go, hey, I have this storm out in West Texas, it's going to be in Austin by 3 p.m. It's extremely hard to say something like that. Really, once these storms are occurring and moving, that's really when you have to make that decision of, this thing might produce a tornado in the next 10, 15 minutes, something like that, which causes problems. It's a short lead time. We can't give people a whole lot of lead time. We say, take cover. It's usually, there's a tornado on its way, take cover right now, this moment. And so there's this desire in meteorology to push that limit and to give people warnings on the order of like an hour or two. And instead of saying take cover right now, we could say, an hour and a half, you have a very strong chance of having a tornado producing storm near your home. Go ahead and figure out your plan now, and people can do a much better job of preparing if they have a better lead time. Specifically, like hospitals and things just don't have that much time. So giving these guys more lead time is really the goal. And that's where these weather models come in, is if you need more of a lead time, you have to guess at what's happening in the future. And that's really the purpose of these weather models, is to try to give these scientists a little glimpse into the future. And that's what I worked on when I was in school. I worked on the Warn-On forecast, which I will bring up very quickly. Boom. Okay, so this is the thing. I'm not going to go through this guy. I'm just going to pull it up and say this exists. You guys can go take a look at it if you want. But this is what I worked on in school. It's the Warn-On forecast system. It's not in operation yet, so real forecasters don't use this primarily. Real forecasters might look at this weather model, but it hasn't been perfected yet, so it's not operational. But yeah, this is actually the specific weather model that we hope is going to help people with tornadic storms. So hopefully this thing can give forecasters an idea of, there are pretty good chance there's a tornado happening in the next 45 minutes, something like that. Okay, well, I think I touched on just about everything I wanted to. So I want to leave you guys with this. My own point was to sort of talk about this tornado warning problem because it's relevant to y'all, but also I just want to take a moment to say that my experience in school was that a lot of the scientists I came in contact with were extremely helpful, passionate people that really just loved meteorology and wanted to talk about it with people. I mean, at the end of the day, these guys are nerds, right? We're all nerds. So if you have any interest in meteorology, science of any sort, even if you're not good at math, it'll you'll find a way to get through it, I promise. I have tons of friends that were, got C's, D's, F's in math in high school and still managed to pull off A's in calculus once they got to college, because the passion really matters at that point. So absolutely, if you guys are interested in this, don't let the math push you away from it. And if you all have any questions for me, I'm happy to answer any questions. Or if you guys just want to talk about storms, I'm a nerd. I like talking about it. Your teacher should have my contact information, and he is more than welcome to give it out to anybody that wants it. Well,